characteristics like Miller capacitance on particular discrete devices. So our outline is we're going to first talk about CV and as a general method and compare it to the nano spectroscopy methods on discrete devices. We'll talk about scanning capacitance and its role in failure analysis and try to describe the capacitance imaging contrast technique as a new method for identifying dopant-type defects. We'll discuss some CV curves and compare CV images that are generated as compared to the shifts in flat band voltages on discrete devices. One other application that we're going to talk about is in the area of embedded DRAM on silicon on insulator type devices, buried trench plates, where the plates are not accessible with conventional probe pads, and with NCVS we're able to measure the shifts in flat band voltages and detect the trench leakage, which we would not be able to do otherwise. And then we'll also talk about the calibration and the limits of NCVS of a discrete device and compare those measurements with a multiple finger test site structure done with conventional CV type techniques. So Andy Erickson will go into the more details of the measurement technique itself. Here's Andy.
Hi everybody, and thanks for attending. We sort of decided to split up the talk a little bit because I'm probably a little bit more familiar with the instrument design as opposed to the application. So when it comes to application questions, if you have any, please just type them in and we can answer them on the fly. And I prefer to have some questions during the presentation. It doesn't cause any disruption to me at all. Let me go into the background of what we mean when we say NCVS and why we would use it. Basically, Terry already talked about how you use a test structure to be able to parametrically characterize process output, whether it's an oxide thickness or different types of capacitance. Look for trap charge, look for flat band voltage, and so on. We don't use CV metrology very much in failure analysis, and certainly not at discrete devices, and the reason is here. You need to raise the capacitance of whatever your test structure is to have around a picofarad at the least of capacitance, but gate capacitance of a minimum scaled MOSFET device is sort of 3/10 of a femtofarad. So that's several thousand times less than what you can measure with a normal CV meter. And I've graphically displayed that for us here. So the CV test structure that you're seeing is actually the one that we ended up measuring for the paper to use as calibration. It has a capacitance of about 6/10 of a picofarad, or 600 femtofarads. There's 270 fingers in it. Only 11 are shown in this image, and if you divide that out, so you get about 2.2 femtofarads per finger. That compared with a discrete device is even larger still. So of course you would parse out a small portion of the gate width that shows up in one finger, as I've shown with the red box, and that's how you end up with that sort of 3/10 of a femtofarad. But you can actually calculate that from first principles by just looking at your gate aux and your gate width of the technology, and that is actually a scaling constant, so everything else gets scaled to maintain that number. So that is the same in a 180 nanometer transistor as it is in a 32 nanometer transistor, within fairly small margins, because it determines the on characteristics of the transistor. So what we've done to sort of talk about this is to say, well, the reason why you're going to use CV instead of simply, say, IV or microscopy, as sort of is traditionally used, is a lot of the defects now in sub 45, 45, 32, even 65, a lot of the defects are related to doping, or at least when you get to a point where you can't figure out what it is in any microscope image, you call it a doping defect because you have no other way of describing it, no other theories. And the idea behind SCM was, or scanning capacitance, was always to be able to highlight that stuff. And a lot of people have such a technique in their labs. In fact, I think we can do with a show of hands how many people who are listening actually are familiar with the technique of scanning capacitance, or perhaps have it in your labs. Can you do that now? I think there's some button you click on that says that you answer yes or no. And I'll go on, but the point here is that capacitance was used to do that, but for doing individual CV metrology, it hasn't really been usable, because the device that we made for digital instruments, and then what was essentially copied or reproduced at other AFM companies, didn't really work very well for CV. It didn't do spectroscopy, and furthermore, the capacitance curves, you really need a second tip for it. But the idea is that you could make some CV measurements using that similar sort of capacitor. So let's talk a little bit about scanning capacitance and what it is, so that when it comes down to it, you'll be able to understand the curves that are in the paper and what contrasts mean, and perhaps it'll help you in the work that you do now. I see that 5 people affirmed that they had capacitance, so it's a reasonable percentage of the attendees. So this is sort of the standard numbers that everybody quotes, 10 to 15 to 10 to the 20. We found that actually goes down to about 10 to the 11th. You can still see the capacitance at a doping range of 10 to the 11, which is like in the range of special power devices and CCD chips. But for FA, it's been particularly useful. You can see if an implant is missing or there, although that system has really failed to function effectively below the 65 nanometer node. There's not that many labs that are able to do things like dopant metrology with a capacitance imaging tool at those kind of levels. This is a depiction of what an SCM sensor sort of in general terms is. There's a resonator that you tune with the tip sample system. You run it at about 1 gigahertz. It oscillates away, and then as that tip encounters some variation in capacitance, it gets damped or excited by that, and that's picked up by a detector, and it runs through some electronics to give you the output. You're going to see 2 different types of signals. One I've highlighted in a red box, a DC cap, and the other one is the output of a lock-in. That would be amplitude and phase, or AC cap. And we'll get into what the difference between those 2 are. But in this next slide, you'll be able to see what AC cap looks like over a test structure. Some of you are familiar with this particular test structure. It's basically just an old technology SRAM that's been HF stripped down to silicon. The tip scans over it. And you can see that I've highlighted the junctions between the wells, and so there's a little stripe there where the contrast is muted in green, green being P, blue being N. Really what the color table is, false color table, showing you the phase of the signal. So there's a stripe between the 2 wells down the middle, and that's a fairly wide junction. And then there's the LED under the gate transistor. I think I can put my mouse over it. This is a transistor here, so the gate would actually stretch across here to there. I think this is a 1/4 micron device, so it's pretty large by what we're used to seeing. But you can see this little, like a halo effect, a little light green. That's the LDD. So that light green is the implant that's sort of tucked underneath the sidewall spacer, and the blue is the channel. And then over here is the NFET device. Of the same type on the other side, and then the well between them. So the junction between the 2 wells you can see very clearly defined here, and then you can see a nice sharp junction right here between the gate underneath the gate. And the reason why it's sharper over underneath the gate is because the doping level is higher, and so the junction width is smaller. So you can see that capacitance at this level is very nicely giving you a nice, bright, sharp picture of the underlying structures in doping. it turns out you can also still look at some transistors. And so this is a 45 nanometer transistor, and I've put in a little structure here to represent the gate, which isn't visible in the capacitance measurement because, of course, well, I think the doping's so high that it doesn't see it anymore so much, and its connection isn't all that good. But you can see the source and drain implants. That would be the light green region, and you can see the junction between them. And since that gate is 45 nanometers, this is a much smaller, smaller structure than the previous one. And so the image will look a little bit more blurry. You can also begin to see the resolution limits in imaging. Maybe we could do a little better with a little cleaner sample prep or something, but basically you can see the structure, you can see the P well or the N well underneath and the P implants up above. You can see the outline of the STI layer where you're getting sort of no signal. And this is okay as an imaging tool. You can sometimes see that an implant would be missing. You can sometimes see that a channel doesn't exist per se. You can see if a well is made properly, and so that forms or that makes a fairly useful tool. But it isn't so easy to use. It takes quite some time to do the sample prep. Your investment in getting to the point of where you produce this picture is pretty large. And what's more, this one was a random one. You can section through any SRAM array and fairly easily see some transistors and pick the one that you like and image it. But getting to the one that's specific to your failure, that's trick. So the sample prep there has got a lot of technique built into it. And of course, you can learn that technique. But what would be really nice is if you could get doping information and trap charge information and gate oxide information and that sort of thing, Miller capacitance. You could get that easily. And then the idea would be that maybe you could go to something at contact layer. So this is an image of a similar technology, well, similar technology size that shows both AC and DC capacitance. So remember on that diagram I showed two different outputs from the electronics. Well, the one on the right is the DC value, so that's just the sensor output. So as the sensor, the tip goes over a structure that it sees as a change in capacitance, its level shifts. So that's a DC, kind of a DC CV curve measurement. And so the image in the right is that. The image on the left is the sort of traditional scanning capacitance or AC capacitance, DCDV, and that is giving you dopant type information. You can see in the right picture you've got a nice bright signal when it goes over any of the well contacts because they're very large capacitance changes, and over the individual inverter or transistor contacts, the capacitance change is somewhat smaller. You can also see that the signal level on individual contacts can be different from device to device. And what it's actually seeing there is the difference in the geometry, I believe, underneath. It can be also the doping concentration of the structure underlying it. And remember that this is a really simple sample to make. It takes just a little bit of delayering. You can spend just a few minutes to get down to contact layer, or a few hours depending on how careful you want to be with it. But everybody routinely makes this type of structure. It's roughly exactly the same as the type of structure that anybody would make in order to do nanoprobing on such a device. Let me ask another question. How many people out there are nanoprobers? How many of you have nanoprobers, whether it's of any style, whether you use fib pads, fib mills, SEM probers, or AFPs? I'd like to get a show of hands so we can figure out where we are. And then I guess also as a show of hands, how many recognize this layout? This is a pretty traditional standard one, so that you can know what you're looking at. Let me move on. The difference in signal between the contacts. Oh, I see we've got 6 nanoprobers out there. Appreciate that. And then I guess also let me ask the other question. And less of those people understand the layout. That's good. I like this. Put a question in and out comes an answer. Let me also ask, how many of you find this this stuff interesting and think you'll be thinking about it in the future? So going on, you can see some contrast differential between contacts. In fact, I would point out these two down here. You can see these two little inverter contacts show a different signal level in the AC curve, and as does another one over here. And probably if we change the contrast a little bit, you'd see subtle differences between them. That's very, very similar to the kind of results that we normally get by doing picocurrent imaging. And I think that in the future, people will use that to point out what is, you know, where a suspect failure would be. And let me also point out for the people who don't understand what we're looking at, this is an SRAM transistor cell, or an SRAM sample that's been delayered, and we have several cells worth of memory in a 60 SRAM. And this one's a fairly aggressively scaled geometry. I'm not at liberty to say exactly what size it is, but it's very deep submicron. All right, now what I want to do is talk about how we get, how the contrast mechanism shows up. How is it that one contact is green and another one is blue, or one contact is white and another one is brown? Let me go to the next slide where we talk about MOS capacitors and where the signal comes from, essentially. So this is a little primer on scanning capacitance. But there's a gate and a semiconductor region and some oxide or dielectric between them. And as you change the bias on the structure, you create a depletion region, which effectively changes some the capacitance or the plate spacing, because as you bias up the semiconductor, either you deplete it out and so the capacitor plates essentially move apart, or you accumulate it so all the charge is tucked up underneath the gate, and so you get a higher capacitance. And the right-hand diagram simply shows changing a large metal gate structure down for a probe tip. So this was always the kind of picture we would show in order to be able to demonstrate the difference between scanning capacitance and MOS test structure measurement. Well, now it turns out with using capacitance voltage spectroscopy at contact level, the left picture is more like the actual picture. So in other words, there is a fully defined metal or polysilicon, although I guess it's metal now, gate structure over some oxide. And so the fringing field effects are going to be the field effects inside of the device itself. So it makes for a nice simplified structure to understand. We've put in a little flash animation to show the bias changing, and then effectively some capacitor plates moving, as I was talking about. And those are represented by the depletion in, say, this N-type semiconductor, where I'm depleting out an area, or I'm bringing it to equilibrium, or I'm accumulating it. And effectively, in the bottom picture, the capacitance would be highest because the charges are closest together. So we get this capacitance between, well, in a MOS structure or in a gate structure. It's voltage dependent because, of course, you're moving charges in and out of the device. And those charge changes can be detected nicely by the capacitance sensor. And keep in mind that the capacitance sensor that we're going to use, it has the ability to see, to create.
Hey, this is Peter Harris. It seems Andy's inadvertently hit the standby button on his computer, so he'll be back in a second when the screen comes on.
Now.
Oh, he's back.
I'm back
okay.
now. Can everybody hear me still? That was a little that was like really dumb that it's a key that allows you to just turn off your computer and stop the session. Anyway, I'm sorry about that. So I was talking about CV curves and moving the charge around underneath them. I was going to say that the capacitance sensor that we use to do imaging with is creating a tiny little device that is a few nanometers on the side, and that's how it creates the image. And the capacitance changes there are lower than attofarads, less than attofarads that you are able to measure in order to be able to create an image. Whereas in these structures which are connected up to transistors, the capacitance there are, like I said, sort of femtofarad levels, or just sub-femtofarad, which is hundreds of attofarads. And so the signal to noise, it can be not so bad. That's how we're able to do such measurements. So we have another diagram here which talks about depletion and versus accumulation. And so to see how this thing works, the top animation refers to what's called the inversion or the low frequency depletion curve, and that is the one that's highlighted in green here. So basically, you've got a depletion down, and then the inversion layer forms, and that'll be the little positive ions that form up underneath the gate. You'll see them here in a minute. Once depletion gets to a certain level, an accumulation layer forms, and the capacitance doesn't change anymore. Whereas when you're moving the signal fast enough, the depletion changes all the way through, and you get into what's called a deep depletion curve. So in the AC capacitance that people typically use, it would be more the set of the curve on the bottom, the deep depletion curve. The reason being that your AC frequency is usually measured in kilohertz, up to maybe 100 kilohertz. What does the capacitance sensor measure? How does it measure it? Typically, it doesn't measure the whole CV curve unless you're taking a spectroscopic measurement. But what we do is we apply an AC bias to whatever the structure is that has this CV curve, and out comes a capacitance change that's in phase with or out of phase with the applied AC signal. And depending upon the CV curve of the structure that's being measured, you'll get, say, a larger signal or a smaller signal. And what's not mentioned in this, what's not shown in this particular animation is, let's see, this is a N-type curve, is a P-type curve, which would have opposite phase going away. So you would measure essentially a phase change. And so that's the difference between what we saw in the previous images of a green versus a blue. So those are simply different phases, because holes will respond in one direction to a signal, and electrons would respond in a different with a different motion. So I hope that this animation helps everybody to see, to imagine what is in the capacitance images themselves, and how we would use them. Now let's look at what kinds of curves we might get out of an actual measurement of a transistor, and find out what we can learn about that. So the thing I want to focus your mind on first is this image, and where the beginnings of these arrows show up. You'll notice a small contrast difference between sort of one that's green and one that's blue, right next door neighbors to each other. These two devices, or the devices underneath those contacts. Again, we're looking at an SRAM array that's been polished down to contact layer and scanned with a capacitance microscope, and we get this anomalous image contrast. So the question is, what is the image contrast between these two contacts? And the only way to really understand it is to take a CV curve at each of those points, because your initial intuition would probably tell you something about just dopant concentration or something like that. But until you take the CV measurement, you don't find out that really the contrast mechanism in this image between those two contacts is actually a flat band voltage shift, which is indicated by the 2 nano CV curves. So that's sort of nano capacitance voltage spectroscopy at work. There's a fairly significant, I think this voltage range is maybe a volt or a volt and a half, and so there's something like 0.3 or 0.4 of a volt difference between these two curves, even though the actual variation, capacitive variation as you go over them is about the same. It's simply you're in the operating point of one with a low signal level and one has a high signal level. And that is what corresponds to the contrast there, not strictly that there's a doping difference, it's that there's a voltage shift. We're still looking at how to calibrate what those structures are. We need to actually have test structures made which are intentionally misdoped and spend more time looking on them. So I'm sure you'll see more papers emerge as we calibrate these effects. But the point here is that there's a very measurable threshold difference or flat band voltage difference, which would result in a very strong threshold effect when the transistor was operated. So when that device was turned on, you would expect to see a significant voltage shift in its on characteristic. And this is being measured with capacitance and highlighted by an image, and then you go to the CV curves. So in this case, like I said, the contrast isn't necessarily coming from the signal level or what is the inherent signal level of that device. It's coming with a voltage shift. So until you keep track or parse out the differences between your bias frequency, your bias amplitude, your sensor frequency, your DC bias levels, you can't really be clear as to what's causing the contrast. And this has, I know, caused quite a lot of confusion out in the field because it's a few things to keep track of. But because now this system is relatively easy to take measurements and also to specify where you're taking the CV curve, where the biasing or reverse biasing effect is taking place, it becomes much easier to quantify and calibrate. What I want to say about that is that in some structures you may want to not just take an image of a structure, or just take a single point image and place that same probe down and take a CV curve. You may want to be able to do a curve specifically between 2 or 3 points where you're reverse biasing, say, the drain of one structure while you're looking at the capacitance of a gate. That's what we're going to do when we get to the calibration portion of this. But there's another part of the paper which I'd like to hand the talk over to Terry to talk about EDRAM structures and what we measured here, because this is an example of where we had multiple probes down and we're measuring capacitance with one probe and applying a bias with a second probe. So perhaps he could take over.
Okay, so the example that Andy's talking about is an embedded DRAM structure where we have a buried trench capacitor. And even though this is silicon on insulator and supposedly shouldn't have a leakage path between the cells, because there is a problem with the buried trench capacitor, we have a leakage path between adjacent cells. And as Andy mentioned, if you have 3 probes down, you can actually plot out the leakage current, and this is done without having access directly to the buried plate itself where the leakage is occurring. So what is seen on the right is an actual plot of the leakage between the 2 buried trench capacitors in adjacent embedded DRAM cells. So the blue curve is a normal trench capacitance, and the red curve is showing the leakage that's occurring between these 2 adjacent embedded DRAM cells. So this is an example where with multiple probes you can actually get quantifiable leakage measurements where you would not have access to the nodes to make the measurement correctly. This is an important characteristic because on embedded DRAM, leakage of the trench capacitor will affect the ability of the cell to retain state and won't function properly if there's appreciable leakage in the cell, appreciable leakage between adjacent embedded DRAM cells itself. So this is an example of where you can practically measure and apply it and localize a specific leakage between 2 leakage embedded DRAM cells. So the next plot is on CV curves and how they can be calibrated. and Andy will talk about that.
Okay, back with you now. I wanted to talk briefly about CV curves and this calibration thing. We'll finish the talk with that. You'll notice that in the previous slide, I'll actually bring it up for a second, this nice C in femtofarads, but the only real calibration that we have here is that a normal cell should have on the order of 30 femtofarads of capacitance. So on that trench, a single trench hooked up to a DRAM cell, or a stack for that matter, the capacitance is typically designed to have about 30 femtofarads of capacitance. But we could use that as a calibrator, but there is no inherent calibration of the sensor itself, so it's not the kind of thing that you just have a dial and you set it to a certain sensitivity, although the idea is that if you could calibrate it, you could do such a thing. All we know is that there's a very striking difference between a leaking failed cell and a normal cell in terms of the capacitance that it's able to sustain. So that is the motivation behind doing an NCVS measurement on a particularly pre-measured test structure. So we showed you a picture of the test structure before. I'd like to highlight out that what we've shown is just a few fingers of a many finger structure in order to get that 0.6 of a picofarad capacitance so that the CV meter can measure it. So you have on the right-hand side of this screen two different sets of measurements. One measured at 110 megahertz, so it's a particular type of CV meter. Which one is that? So that's a 4294, the 110 megahertz capacitance measurement. And then the 30 megahertz measurement is a little bit less accurate, and you can see that it's not measuring exactly the same as the 110 megahertz. And the reason has to do with all the calibration that you go through in order to be able to null out the capacitance of the cables and all the other structures. And the 35 megahertz device is a 4385. Those are both Agilent, yeah. So those devices are typically they're the test structure, parametric characterization test structures. So those are the process monitors that are done. Well, we happened to pull one, or Terry did. IBM was nice enough to pull that out so that they could calibrate it, and he had the measurement. So we know what the capacitance is of that entire test structure. And then what they did was stripped off the metal layers and measured the structure at contact, and what you end up with is this thing being divided up into individual fingers, or say half a finger on one side and half a finger on another. So if you put one probe on any one of the source drain contacts and the other probe on the gate, you'll be measuring just the capacitance between those two gate fingers and the source drain region in between them. So that is 1/270th of this 6/10 of a picofarad test structure. Now we're making an assumption that each of these test structures is particularly uniform, or each one of the fingers is uniform to the entire test structure. So in order to do the calibration, you have to assume that that you can do that. And that's probably not true. I guess one of the next things was to calibrate it. This is just a proof of concept. The next thing would be to do many fingers individually, average them together, and then you've got your calibration, because you know that that the number is going to be off a little bit due to the process variation from finger to finger. One of the other things that you would be concerned about in order to do a calibration is, does series resistance play a role in this measurement? Now, in the case of a test structure measurement, you have to worry very strongly about calibrating things like cable capacitance and resistance of cables and so on. In the case of using this capacitance sensor at the end of an AFM tip, the only resistances that you really have to worry about, because the sensor is right there near the tip, is the series resistance of the silicide that connects the contacts there, and also the probe resistance. And so we've gone to the trouble of just calculating what the oxide impedance would be as seen by the tip on one of these fingers. And so the equation is there with essentially 2 femtofarads and measured at a gigahertz with 1/2 pi. Anyway, you end up with 83 kilohertz or 83 kiloohms of resistance or Z effective in series with something under a kiloohm, probably more like 300 or 400 ohms, including the silicide resistance. And so that effect should be negligible. So that's one thing you probably don't have to worry about when doing these measurements. And that's sort of contrary to the normal test structure measurements with long cables hooked up to boxes. What you do have to worry about, however, is how you operate the sensor. So we've done a little diagram of the capacitance sensor and some probes and shown 2 curves. One of them, the red curve, is fairly noisy, as you'll see, but it has a fairly flat top and flat bottom and a fairly sharp transition. The other curve is a blue curve, which has much less noise, but has a more stretched out transition. So in other words, this is a traditional or a classic CV stretch out, and that tells you that your probing voltage in doing the measurement is causing an artifact in the CV data. And so I guess the red curve and its noise is the price that you pay for being able to measure 2 femtofarads instead of 600 femtofarads, and that is exactly the difference. The way that you make the difference or the differentiation between those 2 measurements, the red curve and the blue curve, is essentially at what operating point do you operate the capacitance sensor, what frequency do you operate it on, and how close to its resonance. By going off resonance a little bit, you can lower the probing voltage at the expense of a little noise, but get a little bit more accurate data. And so that probably is going to lend itself to doing a bit more averaging so that you can clean up the data while still having a very low probing voltage so that the numbers are nice and accurate. On the next one, I have we've plotted these 2 curves relative to each other. The previous 110 megahertz pad level measurement and the noisier NCVS taken at a gigahertz. There's a couple of striking things that you can point to. First of all, the center of the transition is virtually exactly the same as the center of the transition in the pad level measurement. The place that you'd like to calibrate to is probably the flat band voltage, which is circled in the green, and that's probably a little bit closer to, or the area where the circle goes through it, pointing to that which curve is going to which graph. But up near the transition, up near accumulation, is where you want to be checking this. So there's a little bit of an error there, 100 millivolts or so, which probably would be nulled out if we lowered the probing voltage a little bit further. But again, this is a first case study. There is another couple of things I want to draw your attention to, though. One is that the top of the accumulated part of the NCVS curve is quite flat, which is what it's supposed to be. The green curve shows a little turn up when it's in accumulation, and the reason for that is something that these kinds of test structure measurements of capacitance struggle with, and that is because of leakage in the very thin gate oxides. So when the leakage happens, it kind of swamps the capacitance signal that is in that instrument, in the Agilent box, and so they find themselves having to calibrate that out, and it forms a real problem with being able to pick off exactly when the transition occurs. So it's not clear that the green curve is wholly without artifact. In fact, they go to great lengths in those types of parametric measurements, and in the end, mostly what they do is compare it to the previous lot. So there's some errors there in that box, and the reason why the gigahertz sensor isn't susceptible to that is that it is a resonant sensor instead of a bridge. The resonant sensor isn't loaded down with a little bit of gate leakage. It doesn't really care. It just passes through the sensor to ground, and so it doesn't really bother it that there's some gate leakage as you accumulate the gate oxide. So the point behind this is that we've shown that the transitions are roughly the same, and that you can, at the very least, calibrate down to the overall transition size. It's, like I said, 2 femtofarads versus 600 femtofarads at the expense of a little bit of noise. But now you're able to do this in a way such that you can look at a discrete device, measure its capacitance, measure its neighbor's capacitance, and have some confidence that you're measuring an accurate number, and that you're able to do that. And then furthermore, with some careful calibration relative to these sorts of test structures, you can actually calibrate the numbers that are coming out of the machine given a certain set of operating conditions. And that is something which I would expect to grow out of the use of this technique, and I think that we might find it, the community might find this a valuable and interesting place to take failure analysis, so that we can move from measuring full devices and just measuring their IV curves to measuring dopant defects that you couldn't hope of seeing. Such as subtle threshold variations. You couldn't hope of seeing that in a scanning capacitance micrograph, but doing a CV curve, a spectroscopy curve on that particular portion of the device will probably yield a lot of understanding about the doping and allow the Pareto to be filled in with those doping defects in a far more clear way. And so that's sort of the talk. We're going to break for questions in a minute, but I'll just summarize as to what we've talked about. Actually, I'm going to just hand the microphone over to Terry so he can summarize the uses that he sees of this technique.
So, then you mentioned we've demonstrated the ability to match the measurements that are typically done at pad level CV measurements with those with resonant sensor at a discrete device level. And as Andy mentioned, the subtlety of the devices or the defects in devices, as we were talking about sub-45 nanometer type technologies, we have to be more conscious of dopant type fluctuations. And we have to be sensitive to the idea that we have a method for measuring those fluctuations. So we validated the NCVS measurements compared to a test site structure, and that we also see that NCVS techniques will be applicable to discrete devices on both scaled gate oxide films as well as high K dielectric type films. This is, of course, a huge improvement over our techniques that we've traditionally employed. Okay, sure. We have a little microphone problem here. So basically, we've shown that we've matched the pad level measurements of a test site structure with the discrete NVCS measurement. We've also shown that these types of techniques at the discrete device level will enable us to troubleshoot and identify slight problems associated with dopants, as well as gate oxide film problems at sub-45 nanometer technologies. So in conclusion, the nanoprobing CV scanning capacitance imaging is accomplished without changing the sensors. It's done at a CA contact level with a minimum amount of sample preparation, and it is complementary to atomic force probe current imaging for rapid defect isolation. So it's another imaging type technique in addition to AFP current imaging. The introduction of nano-CV metrology and scanning capacitance with nanoprobing current imaging enables us to detect at CA level with a minimum amount of delayering such as frontal line defects as dopant level fluctuations, deep trench capacitor leakage type characteristics, as well as gate oxide leakage fails in themselves. So that's the summary of our paper, and if there are any questions, we'll be happy to entertain them now.
Thanks, Andy, Terry. It was very interesting. There's a couple of questions in already, which I'm going to forward to Andy. If anybody has a question that they'd like to ask directly, then please raise your hand, and I can unmute the microphone and you can ask that. If you don't feel comfortable with that, then by all means just type the question and I will forward that that question to Andy and Terry.
Okay, I see a question. Sorry?
That's okay. I was just going to say, do you see that question, Andy?
Did you? The question is, did you use 3 probes to measure the CV or 2 probes? Is the test structure on bulk or SOI, and if so, what technology? Yeah. Okay, on which one? Okay, so the NCVS on the test structure was a 2-probe measurement between the gate and the source drain region. That's all that was necessary, and it was on an SOI sample. Can you talk about the technology? So that's a 65 nanometer structure.
Do we have any other questions? Okay, there's a question from Yuk Sang. Yuk, you should be able to speak now.
On measuring the gate capacitance, how do you achieve that in SOI transistors without the body tie?
Okay, so the question is if you have an SOI transistor and you don't have a body tie to the backside contact, how would you carry out a CV measurement? So many of the structures that you saw were actually SOI. There's 2 parts to this answer. First of all, for being able to get the signal through the box region or the isolation region, it doesn't really matter because, as you know, capacitors in series, only the small one counts, and the small one is typically always the one that you're measuring. Mm-hmm. And so that bias voltage or the gigahertz dissipation into the sample, either of those will easily transmit through the box layer because its capacitance is fairly significant compared to the very small capacitances that you measure. And
okay.
So from an imaging purpose, the measurements that you do, it doesn't really affect it that it's on the box. Mm-hmm. For the quantitative CV measurements, typically you're going to use 2 or 3 probes in order to be able to do those measurements. So you're going to place a probe on a source and a probe on a gate and measure the capacitance directly between those 2, or a probe on a bulk on a P-well or something relative to a gate. Mm-hmm. So that's the way that you'll carry out those measurements. Does that answer the question?
Yeah. So I have a follow-up question on that.
Please.
Suppose I would like to decouple the capacitance between the gate and the Miller capacitance in the SOI transistor, like in SRAM, for instance. So how can we decouple them?
So when you want to decouple the Miller capacitance, so which capacitance did you want to measure?
So I would like to know the gate capacitance and the Miller capacitance
separately
in SOI, right, transistor.
So does your well contact have a
There's no body tie.
So there's no body tie.
In other words, the body is floating. Yeah.
Well, I think what you're going to end up doing is grounding or applying bias to a source or a drain or to the gate itself, and then having a body contact, because I think there's still the capacitance between the gate and the body is still the small one relative to the one that goes through the box layer. I'm not so sure about that. I think that's going to be an instrument setup. I think it's a tricky measurement, is what I would say.
Yeah, in a typical SOI SRAM cells, there's no body tie. Right? So I just don't know how to decouple those components.
Well, like I said, I think you can also use the connection. There's still a connection to the box layer. It doesn't matter that there's an isolator in between. That's just another capacitance in the series. And to my understanding, depending upon how many devices are into the body or the well that's there, those are often longer structures, and so they would have significant capacitance. And then it would just be a correction to that number.
Thanks, Jörg. I think there's a couple of other people with questions, and I'd like to just give them a chance. Christian, if you're still there, I have enabled your microphone so you can ask Andy the question directly.
Hi, Christian. Go ahead, Christian.
Maybe Christian doesn't have a microphone. He's typed his question, Andy, so yes, Christian doesn't have a microphone. So he'd like to know how far is the technique scalable, and is the limitation, what's the limitation of the AFP?
So I'd like a little clarification on the question. So scaling which portion of the technique? We're talking about the imaging or the CV curves?
I have to wait now for Christian to type that. Imaging.
Okay, for the imaging, I showed a 45 nanometer transistor, so you can imagine that that it's getting tricky to get a 32 on there. I've not actually tried to do one on a 32 nanometer transistor to do an imaging of the cross section at silicon level. You can kind of see what the resolution is there. It's probably 5 or 10 nanometers on that in that presentation, which will be up on the website, or you'll be able to view it again if you need to. In fact, I can just bring that up now since we're talking about it. So this is a 45 nanometer transistor. You can imagine a 32 would be 70% the distance there. So if that resolution is significant or is sufficient for you, maybe that technique could work. At the imaging at contact level, I can tell you that it certainly scales down to 22 and probably below that. So at contact level, the nice thing is the capacitances that you end up measuring are really one of the constants in the scaling equation. So even as you shrink the gate length or the depth of an implant, you change the actual charge stored in that implant or in that gate, or you maintain that by changing doping or thinning oxides, and so that's a constant. So there isn't a limit in terms of doing the measurements at contact level and doing CV curves.
Thanks, Andy. Did you see the question that I forwarded from the second question?
No, I do not see
so
that.
So the question is, were the source
I do.
drain...
Were the source drains shorted when measuring CV on the test structure? Let's bring that picture up. That's a very good question, and on first viewing, it would be unlikely that you'd catch it. The way this test structure is made is that you've got a source drain region here, which is like a single source in between two gates, and then the gate itself is it surrounds it, so it's almost like a ring structure. So you don't actually, nothing is happening at the source and drain above or below this part of the structure. So you only need two probes to be able to fully characterize. You're essentially characterizing half on one gate and half on another.
Okay.
Does that answer the question?
I'm waiting for an indication. I think not many people have microphones. Are there any other questions? Either a show of hand or a typed question. Okay, I'm not seeing any questions. So Andy, I think a thank you for you and Terry for a very interesting presentation.
Yeah, well, thanks very much for your attention and listening.
I've just received a follow-up question from the last the last question, so I'll send that to you, and then maybe we can end with the answer to that.
Where is that? There we go. Pad cap normally have source drain. Yes. Well, this is effectively the same thing. as the short source and drain being shorted, because of course the gate separates the source drain regions, but we're making contact to all of the gate fingers and therefore controlling the charge on them, and the only place that we're varying the charge is in the source drain region. So it's really a single pad test structure. You could easily do it with two, of course, and just control the source and drain independently. That's fine, but this one in particular is a 2-probe measurement because the test structure wants that.
Okay, well, thanks, Andy, and thank you for the attendees. With that, we'll.
I'm gonna hand the microphone over to Terry so he can say thanks too.
Thanks to everyone for joining us, and we'll have this posted on the website, and everyone can review the presentation and the individual foils that we've talked about. Yes, you can email either one of us if you have any other follow-up questions. So here's Andy.
All right.
Okay. Thank you very much. And with that, we'll end this this webinar. Thank you.
Have a good day.